This is a second lecture from Chapter 13, Kinetics. In the Intro to Kinetics, we talked about expressing the rate of a reaction. And remember, the rate is defined as the change in concentration of any reactant or product over change in time, over a certain amount of time. That is the rate. We are going to, in this lecture, talk about rate laws. Okay, that is different. So please remember that the rate is this, units molarity per second, and rate law is going to be a little different. Think of the rate law as a function, as a formula that will allow us to have input and output, okay, to plug in different variables of a reaction and get different values out. Right, so a rate law has the generic form shown right here. The rate is equal to some rate constant, K, just a proportionality constant, times the concentration of each reactant raised to some exponent. Now, I want to make something very clear. It's very, very important. And that is that these exponents, the only way to know what they're equal to is to do an experiment in the lab with this reaction and monitor rates. Those are called order of reaction. We'll talk about those in a bit. But these coefficients in a balanced reaction have nothing to do with the exponents. Completely unrelated, okay? That's very important to keep that in mind. So again, looking at the general format for a rate law. This is the function describing rate. Rate equals some rate constant, which will end up being very important. And the exponents, again, are called the order of the reaction with respect to whatever reactant or product they modify. So we would say the order of reaction with respect to A is little a. The order of the reaction with respect to B is little b. The overall order of the reaction is the sum of all of the exponents. So in this case, it'd be A plus B. Now I want you to think for a minute on the importance of these exponents to the overall rate. What do these exponents do mathematically? They modify the importance of concentration to the overall rate, right? The more important the concentration of a particular reactant is to the rate of reaction, the larger the exponent's going to be. What if the exponent was 0? What would that say? Well, anything raised to the 0 power is 1, right? An exponent of 0 would mean that reactant is not important at all to the rate of reaction. Right, one of the first things we're going to try to do is give you experimental data and explain to you how the orders of reactions are actually found. Once we find the order of a reaction, those exponents, we can then plug in values and solve for the rate constant. And finally, whoopsie daisy, and finally, the rate law, these rate laws, just call the rate law later on, we'll call them differential rate laws, but the concentration of products do not appear in this rate law because these rate laws are for initial rates only. Remember, when the reaction first starts, there's no significant amount of product, and it's much more simple then to talk about the rate and the things that affect it. So going through the different orders, the different exponents that could have, they're typically this is just me, from what I've seen, the values of the exponent 0, 1, and 2 are by far the most common, okay? It doesn't really get much higher than 2. And you'll see when we get farther into this chapter the order of the reaction is going to tell you how many times this particular reactant, in this case A, how many of them have to collide to get the reaction to occur. So it's pretty rare that you're going to get, for example, 3 or more reactant A's colliding with each other at the same time. Alrighty, so if the exponent or the order of reaction is 0, as we said before, that means that that particular reactant has no effect on the rate of reaction, right? Because anything raised to the 0 power is 1. If n equals 1, okay, what does that mean? That means that the rate would simply equal k times the concentration, right? If the exponent's 1. And what does that mean? That means then that rate is directly proportional to the concentration of that substance. So if we double the concentration of that substance, we double the rate as a direct proportion. So you're going to be looking at tables of data shortly, so it's important to kind of understand what these different orders mean so that you can look at the table and make conclusions. Now, let's say the n is 2, so that you end up with an expression like this. Your exponent is 2. What does that mean? That means that every time we, let's say, double the concentration of A, what's going to happen to the rate? That 2 is going to be squared, okay? So that means the rate would increase by a factor of 4 if you doubled the rate. What happened if we tripled the concentration of A and it was second order? Well, what's 3 squared? That would be 9 times faster rate. So that means that the reactant A is extremely important to the rate of the reaction. The higher the order gets, the more important that is to the rate. So here's kind of a summary. Again, if it is first order, it's directly proportional. Whatever you do to the concentration of that substance, you'll do the exact same thing to the rate. If it is second order, you are going to square to get the effect of the rate. I should have put, I don't want you to start doubling those. So let's say, I should have included that. If you triple the rate, okay, so it's a square effect, not a doubling effect. And for 0 order, that means that substance has no effect on the rate at all. So the rate changes, or excuse me, the rate doesn't change. It stays what it was. All right, so we're ready to look at some actual data, and you might actually do a lab on this. I don't know if they've stopped it or if they still do it, but it's called, the lab method is called the method of initial rates. Remember that this rate law, we're going to learn a second type of rate law later on called the integrated rate law. But this initial rate law is for just the initial rate, and we're only looking at reactants. The data that's collected in the lab is the concentration of the reactant, okay, versus the rate of reaction. So, and what we're looking for is what effect does a change in concentration of a reactant have on the overall rate? And by looking at how sensitive each reactant is to the rate of reaction, we'll be able to determine the orders of reaction. So here's an example. Here's the reaction we're going to look at. So we know the generic expression for the rate law is this, and we're trying to find the order of reaction with respect to each of the reactants. This is the data that was collected. So for the method of initial rate, several experiments have to be run. Each experiment has a change in concentration. So if you compare experiment 1 and 2, what have we done differently? We've increased the concentration of oxygen gas and then measured the rate. Again, what have we done, let's say, between experiment 1 and 3? In this case, we have changed the concentration of nitrogen monoxide, okay? So let's now determine the effect from this data. Let's determine the effect on the rate of each of the reactant concentration changes. So An easy way is to literally look at the table and find a situation where the concentration of one of the reactants changes but the other one doesn't. So let's compare experiment 1 to 3. So the concentration of nitrogen monoxide changes by a factor of 2, comparing experiments 1 and 3. Make sure all the other reactants are held constant so that you're only looking at the effect of one of them. So now what happens, hey Gracie, sorry. So what happens to the rate comparing experiments 1 and 3? So you're comparing these two. And the rate for experiments 1 and 3 increases by a factor of 4. So we have when the concentration changes by a factor of 2, the rate changes by a factor of 4. So now let's look at the rate expression. Let's just look at, I'm going to put the proportional sign there. Let's just look at part of it. Okay, let's look at NO, which is what we're looking at now. So what we just found from this table of data is that when we change the concentration of nitrogen monoxide by a factor of 2, the rate changes by 4. So what does M, the order or the exponent, have to be? So you can think of it, simplify it. 2 to the M equals 4, right? Because we're just looking at the changes we made. So what does M have to be for this to be true? M has to be 2. So it is, in fact, second order with respect to nitrogen monoxide. Now let's go ahead and do that for the other reactant, oxygen gas. So let me erase what I have for nitrogen monoxide. And the first thing to do, of course, is define which experiment you're going to compare. So we want to pick an experiment where the concentration of oxygen changes, but the concentration of nitrogen monoxide is constant. So let's compare experiments 1 and 2 because it's constant for nitrogen monoxide. So the concentration of oxygen, gosh, so now I've got to put that in my calculator, don't I? Changes by a factor of 0.066 divided by 0.025. All right, so that is a factor of 2.64. We increased oxygen. What happened to the rate when we did that? So let me do that real quick. And that increased by 2.56. Oh, they're the same. All right, so if I just round it, increased by a factor of 2.6. Experimental data isn't going to be perfect, okay? So don't worry if it's off a little bit like this. But if I round them both to 2 sig figs, they both increase by the same amount. So looking again, let's look at our rate law again and just simplify it. Okay, so to just have the oxygen component. So what did we do? We increased this by 2.6, right? And the rate also increased by 2.6. And we want to know what N has to be for that to be true. Okay, so N clearly has to be 1. All right, so what have we found? We have found that the order of reaction with respect to nitrogen monoxide is 2. The order of reaction with respect to oxygen gas is 1. So the rate law for this reaction is right here. You just plug in the exponents that you found, and if the exponent's 1, you can leave it off. Of course, it's understood. Here is another one. These can be tricky at first, but then they're kind of fun. They're almost like a puzzle, I promise. They're yeah, but just to give you a feel. So here we have 2 reactants again, and our generic rate law, right, would be concentration of ammonium ion raised to some power times concentration of the nitrite ion raised to some power. And we're going to look at the data and try to find. So let's look for the ammonium ion first. So if we compare experiments 1 and 2, we can see that concentration of ammonium ion doubled What happened to the rate? You gotta remember to make sure the other one stays constant, which it does. The rate also doubled. So that tells us that it is first order with respect to the ammonium ion. And now let's look at the data for the nitrite ion. And nitrite ion, remember you want to pick two experiments and you want the concentration of the other one to be constant. So looking at experiments 5 and 6, we can see that when we double the concentration of the nitrite ion, what happens to the rate? The rate also doubles. So they are both first order. And so if we were to write the rate for that, we would get this. They're both first order, right? So you just leave the exponents out. It's understood. The overall order, remember, is just when you add the orders of all the individual reactants together. So the overall order of this reaction is 2. Now that you have the actual rate law with the orders, you can, using that same table of data, you can find out what K is, the rate constant. Alrighty, so you go to any of the experiments in that table of data. I usually just go to the first one because it's just easy, but you'll get the right answer with any of them. And you plug in the information to your rate law. So what is the rate for experiment 1? It's 5.4 times 10 to the minus 7. Remember the units for rate, right? Molarity per second. All right, equals K, which is what we're solving for. The concentration of NH4 for experiment 1 is 0.01. Concentration of nitrite ion is 0.2. Plug all that in, rearrange it, and solve for K. Now, units are critical. Units are critical, so you need to, when you start practicing the method of initial rates in that worksheet, make, even it doesn't ask you, solve for K and make sure you have units. It's useless to have a value of K without the units included. So I'm going to show you the proper way to figure out units, and then I'll give you some shortcut memory ways, okay? So as you rearrange, keep units in everything. The units for rate, molarity per second. The units for each concentration, right, are just molarity. So one of the molarities canceled. So what are the units you're left with here? You are left with 1 over seconds times molarity, right? You've got the seconds and you have one of the molarities left. This is equivalent, hopefully you remember this from math, right? If you have an exponent of -1, it's equivalent to just saying 1 over that value, right? So you will find as you practice that the units for any second order overall reaction, remember they were each first order, will always have the units of seconds to the -1, molarity to the -1, always. So that's my little memory thing. You can memorize, and I'll show you a pattern in how the units change depending on the order of the overall reaction. But for now, go ahead and practice the method of initial rates because we'll be going on to integrated rate laws, and they're a little bit trickier than this. But that's it for this lecture.